Good day, everyone. In this video, we are going to discuss about the proof of equivalences. So if we have this statement P, if and only if Q, then how can we prove the validity of this statement? So we already established that P, if and only if Q, is equivalent to P implies Q and Q implies P, right? So hence, if we can prove that this is true, we can say that P and Q are equivalent. So these steps are constructed using rules of inference, axioms, lemmas, definitions, proven theorems, etc. So to understand that, let us have an example. So n is even if and only if its square n squared is even. So how can we prove this biconditional statement? So again, before we start, we always have to begin with a definition of terms. So what is an even number? So n is even if there exists an integer k such that n is equal to 2k, wherein we can say that a number is even if it is divisible by 2, or if it can be factored out by 2 times some number k. All right. So expressing n is even if and only if its square is even into its equivalent P implies Q and Q implies P statement, we have the following. So P implies Q can then be if n is even, then n squared or its square n squared is even. Meanwhile, if Q implies P, then we can express it as if n squared is even, or if its square is even, then n is even. So if we can prove that P implies Q and Q implies P, then we can prove the validity of this theorem, or if and only if theorem. So the proof for P implies Q goes this way, since we will be using a direct proof. So in proving equivalences, we can use other proofs that we have already discussed. So we can use direct proof, indirect proof, proof by contraposition, as well as proof by contradiction. Okay, so in this case, we are going to use the proof by direct proof, wherein we begin with the premise n is even. So assuming that n is even, and this is true, we then assign n is equal to 2k for some integer k. And using the assumption that n is even, then let us try to prove that n squared is indeed even. So taking the square of the both sides, we have n squared is equal to 4k squared. And we can rewrite 4k squared as 2 times 2k squared, or factoring out the 2. So we can then express it as 2m, where m is equal to 2k squared. So we have proven that n squared has a factor of 2, or that n squared is divisible by 2. So we can say that n squared is even. So by the assumption that n is even, we have proven that n squared is even. Now, let us try to prove Q implies P. So if n squared is even, then n is even. So in this part, we will try to start with this statement n squared is equal to 4k squared. So taking the square root of both sides, okay? So we will be left with n is equal to the square root of 4k squared. And the square root of 4k squared is equivalent to 2k. And as you can see, it has the form of 2k, which means that n is an even number. So in this case, we have proven that P implies Q is true and Q implies P is true. So we can say that this theorem, n is even if and only if its square is even, is also true. Okay. So we can express that using this symbolic form. P implies Q and Q implies P is true and true. So then P if and only if Q is also true. Okay? Sometimes a theorem states that several propositions are equivalent. So such a theorem states then that P sub 1, P sub 2, until P sub n are equivalent. So we can write this into the symbolic notation. P sub 1 if and only if P sub 2 until P sub n. So this equivalence of several propositions is equivalent to a series of implications, wherein P sub 1 implies P sub 2, and P sub 2 implies P sub 3 until P sub n implies P sub n. Because if P sub 1 implies P sub 2 and P sub 2 implies P sub 3, then it also follows that P sub 1 implies P sub 3. Okay, so we can easily prove the equivalence of several propositions by following this form, which is much easier to prove than P sub 1 implies P sub 2 and then P sub 1 implies P sub 3, or that P sub 2 implies P sub 1 and that P sub 2 implies P sub 3, and so on. So this will be a much shorter way of proving this equivalence. Okay, so if we can prove that this is true, then we can also prove the equivalence of the several propositions. So to show you what it means, let us try to prove the equivalence of these three propositions. If P sub 1, then n is even. Then P sub 2, n minus 1 is odd. Then P sub 3, n squared is even. So we can prove that first by proving the conditional P sub 1 implies P sub 2, which then states that if n is even, then n minus 1 is odd. And P sub 2 implies P sub 3, which states that if n minus 1 is odd, then n squared is even. And lastly, P sub 3 implies P sub 1. So if n squared is even, then n is even. So if we can prove that all these three statements, all these three conditionals are true, then we can prove that these three are logically equivalent. So prove these statements about the integer n are equivalent, starting from the first na conditional, P sub 1 minus P sub 2. If n is even, then n minus 1 is odd. So we can essentially use a direct proof to this, starting with the first na premise, n is even. So assuming that this is true, that n is indeed even, then n is equal to 2k. So using this premise, then let's prove that n minus 1 is odd. So if n minus 1 is odd, it follows that it is equivalent to 2k minus 1. Since the value of n, which is equal to 2k, was from this assumption that n is even, okay? And then we can rewrite it into 2 times k minus 1 plus 1, and wherein we can rewrite it into the form of 2m plus 1, where m is equal to k minus 1, wherein this form is an indication that it is an odd number. Okay, so how did we arrive to 2 times k minus 1 plus 1? So we can evaluate this if we distribute 2 to this quantity k minus 1, so it will evaluate to 2k minus 2 plus 1. And this will be equivalent to 2k minus 1, which is equivalent to the first expression, 2k minus 1. Okay, so we have proven the validity or the truth of P sub 1 implies P sub 2. Now let us try to prove the validity of P sub 2 implies P sub 3, which states that if n minus 1 is odd, then n squared is even. So we start with a premise that assuming n minus 1 is odd. So if n minus 1 is odd, then it is equivalent to 2k plus 1, using the definition of an odd number. And then transposing one to the other side, we will be evaluated with this result, 2k plus 2, okay? And then taking the square of the both sides, So now proving that n squared is even. So this will evaluate to 4k squared plus 8k plus 4. And factoring out the 2, then we'll arrive to 2 times k squared plus 4k plus 2, wherein we can rewrite it into the form of n squared is equal to 2m, where m is equal to k squared plus 4k plus 2. So since this has the form of an even number, so we have proven that n squared is even given that n minus 1 is odd. And now for the third na conditional, p sub 3 implies p sub 1, which states that if n squared is even, then n is even. And it will be much easier to prove if we started with the conclusion, which is n is even. So in other words, it is much easier to prove this using contraposition or using the contrapositive of this conditional. And the contrapositive of this statement will be if n is odd, then n squared is odd. And if we can prove that the truth of that contrapositive, then we can also prove that the p sub 3 implies p sub 1. So in other words, what we want is that not of p sub 1 implies not of p sub 3. So we start with not of p sub 1, which is n is odd, assuming that n is odd. So if n is odd, then n is equal to 2k plus some for some integer k. And using that, we will use to prove that n squared is odd. So n squared is equal to 2k plus 1 quantity squared, taking the square of this equation. And then we will have n squared is equal to 4k squared plus 4k plus 1. And factoring out 2 from the first two terms, we'll have 2 times k squared plus k plus 1. And we can rewrite it into 2 times m plus 1, where m is equal to k squared plus k. All right, so since it has the form of an odd number, so we can say that this number, or n squared, is indeed odd, given that n is odd. Since we have proven this statement through its contrapositive, then we can say that p sub 3 implies p sub 1. And since we have shown that all of these three implications are true, we can then conclude that these three propositions are equivalent.